Good morning, students. Welcome to Computer Aided Design course code P20DE102, Week 3, Lecture 3, course discussion topic on curve manipulations. I am RAKESH, Assistant Professor in Department of Mechanical Engineering, Kids Warangal. Before going to enter this topic, let us see the lecture outcome for this topic. After completion of this lecture, student will be able to identify the implementation of curve manipulations in CAD/CAM software. The second lecture outcome is analyze curve manipulations techniques in CAD/CAM system. Let us move to the topic, that is curve manipulations. Analytic and synthetic curves essential to wireframe modeling have been discussed in previous lecture. The effective use of curves in a design and manufacturing environment depends mainly on their manipulation to achieve goals. A user might want to blend Bezier and B-spline curves. Here, these Bezier and B-spline curves are also called as synthetic curves. Bezier and B-spline curves with a certain continuity requirement are the intersection of two curves in a space coordinates. An important point to engineering calculations or modeling of a part. You can see here the following are the implementation of curve manipulations in CAD/CAM software. First one, displaying. Second one, evaluating points on curves. Third one, blending. Fourth one, segmentation. Fifth one, trimming. Sixth one, intersection. Last one is transformation. In the next slide, we will briefly discussing about each and every manipulation tool in CAD/CAM software. Let us see the first one, displaying. Displaying means it's showing the image on the screen. It's showing points, lines, or curve, or surface, or solid, any object. It's showing on the display. Displaying curves provides a designer with a means of visualizing geometric models within limits of the wireframe modeling technique. It also showing different colors. Various colors can be assigned to various curve identification. You can take any software like AUTOCAD, Creo, CATIA, or SolidWorks. With the help of properties tool, we can change the line color or curve color or surface color or solid color. To display a curve, closely spaced points are generated various values of parameter with respect to parameter u. The curve parametric equation is obviously used to generate the coordinates of these points. The display processing unit receives these coordinates and changes them to two-dimensional coordinates related to the device coordinate system of the display terminal. The resulting points are displayed and are connected by short line segments. Line segmentation hardware exists for creating and displaying these line segments. For example, to display straight line, the two endpoints, you can take any line, it connected with the two endpoints and fed to the line generation hardware to generate intermediate points and connect them by short line segment. Here line means the shortest distance between two endpoints, that is called line. Equations of curves such as circles, already we know, we discussed it in the analytical curves. Equation of circle is x square plus y square equal to r square. And conic sections. Conic sections are parabola, hyperbola, ellipse, etc. that involve trigonometry functions are usually rewritten to minimize computation time to generate points on these curves for display purposes. This is the brief discussion about display. The second one is evaluating points and curves. Points and curves are generated for display purposes. Already we discussed in previous slide. For example, finite element modeling techniques requires generating nodal points on the model to be used later in finite element analysis. For doing calculation in finite element method, the given element is uh, first we need to draw the free body diagram for the given element. That means line is connected with, for example, I'm taking one element. Each element having two nodes. The element is connected with two nodes. These nodes later we can do the analysis in finite element analysis. The next point is, in most CAD/CAM systems, the function of evaluating points and curves is made available to the user via generate point on command for its equivalent. It is also mentioned in the previous slide, that is a curve parametric equation is used to evaluate points on it. Evaluation methods must be efficient and fast for interactive purposes, as well as capable of producing enough points to display smooth curve. The obvious method of calculating the coordinates of points on a curve by substituting successive values of its parameter into its quotient is inefficient. So that's why we are moved to the incremental method provided for more efficient. Uh, we'll discuss one example in the classroom. The next one is blending. This is also very important manipulation in CAD/CAM software. The construction of composite curves from the various types of parametric curve segments form the core of blending problem, which can be stated as two curve segments. Let us take first curve, that is P1 of U1. The limits of first curve is 0 to A. Let us take second curve P2 of U2. The limits are 0 to B. That means 0 less than U2 less than B. Find the condition for the two segment to be continuous at the joint. Here notice that the upper limits on U1 and U2 are taken be A and B. U1 upper limit A, U2 upper limit B. The lower limit is both are having lower limit is 0. For general, B-spline curve have an upper limit that is not unit in general. Here, let us take three classes of continuity and the joint can be considered. The first is C0, that is continuity. That is that means ending point of the first curve. Let us take one curve. This is the first curve. The ending point of the first curve and the starting point of second curve. Let us take one more curve. This is the starting point of second curve. The ending point of first curve and the starting point of the second curve are the same. This gives P1 of A equal to P2 of 0. That means first curve upper limit is A and second curve lower limit is 0. So P1 of A equal to P2 of 0. Thus, if the two segments are to be C1 continuous as well they must have slope continuity. The second one is it must have slope continuity. That means differentiate of this first equation. P1 dash of A equal alpha 1t. Second one P2 dash of 0 A equal to alpha 2t. I think this is 0. P1 dash of A equal to alpha 1t, P2 dash of 0 equal to alpha 2t, where alpha 1 and alpha 2 are continuous and t is the common unit tangent vector at the joint. Another example is the blending of Bezier curve and open B-spline curve for slope continuity at the joint. The last segment of the control polygon of the former and the first segment of the control polygon of the latter must be collinear. The third useful class of continuity is if the curvature, that means C2 continuity, is to be continuous at the joint in addition to position and slope. To achieve curvature, continuity is less straightforward and requires the binomial vector to a curve at a point. Let us take one curve. The starting point is u equals 0. This is the end point u equal u max. Let us see the terminology. This figure shows binomial vector of a curve. That here t is the unit vector, unit tangent vector, n is the normal vector. That means unit normal vector. O is the center of curvature, and the radius of curvature at p is rho on a curve segment. Now we can write the curvature at p. The curvature at p is defined as 1 by rho. The binomial vector b is defined as b equal to t cross n. B equal to t cross n. It gives the curvature at p. The next one is segmentation. Segmentation means splitting of a curve. Or divide curve. Segmentation is defined as replacing one existing curve by one or more curve segments of the same curve type, such that the shape of the composite curve is identical to that of original curve. Segmentation is a very useful feature for CAD/CAM system. It is implemented as a divide entity command. The use of divide entity command, a model cleanup for drafting and documentation purpose is an example where an entity might be divided into two at the line of sight of another curve. One of the resulting segments is then removed or blanked out. Another example is when a closed curve has to be split for modeling purposes. Consider the case of creating a ruled surface using a closed rectangle and a circle as a rail of surfaces. Let us take one circle. I want to divide this circle for modeling purpose with the help of this rectangle. By using these two diagonals, we can divide this circle into four segments. This is the one segment, this is the second segment, this is the third segment, this is the fourth segment. 1, 2, 3, 4. This here is segmentation of a circle for modeling purposes. The next one is I am taking one more example. Here I have taken one curve. To split a line connecting two points P0 and P1 at a point P2. Let us assume this is the P0, this is the P1. Connecting two points at point P2, this is the P2. All that is needed to define two new lines lines connecting the points pair is P0 to P2 one pair, another pair is P2 P1. For circles and conics, the angle corresponding to splitting point together with the starting and ending angles of the original curve define the proper range of parameters u for the resulting two segments. This figure is a reparameterization of segmented curve. Uh, Let us take first segment. Write the formula for parametric representation of curve for first segment. That is u equal to u0 plus u1 minus u0 v. The second segment u1 plus um minus u1 into v for second segment. It is clear that here v equal to 0 and v equal to 1 corresponding to proper u values as required. That means u v equal 0, v equal 1, here also v equal 1. The next one is trimming. Trimming curves or entities is a very useful function provided by all CAD/CAM systems. Trimming can truncative or extended a curve. Trimming is mathematically identical to segmentation. The only difference between the two is that result of trimming a curve is only one segment of the curve bounded by trimming boundaries. The trimming function requires evaluating the equation of desired segment of the curves, deleting the original curve, and then storing and displaying the desired segments. Let us take one example. Here first figure show the truncated curve, that means extension of curves. The second one is extended curve. You can see here the first curve u equal to u0, end point is u equal to um. With the help of trimming tool uh, we can remove the unwanted line portion. With the help of extend curve we can extend from um to u equal to u2. Extending general curves such as cubic splines, bezier curves and B-spline curves may not be recommended because the curve behavior outside its original interval u equal to u0 less than u less than um may not be predictable. Let us see the next one, intersection. Here I'm taking two curves. One is the P of U curve, second one is Q of V curve. The intersecting point is P1. At that point P1 U equal to Q1 of V. Intersection of two parametric curves in space. The intersection point P1 of two parametric curves, that is P of U, second one is Q of V, in three-dimensional space require the solution of the following equation in the parameters u and v. Already we know that is P1 u equal to Q1 v. So we can also write as P of u minus Q of v equal to 0. This equation represents the three scalar equations that take the polynomial nonlinear form, generally in the two parameter unknowns. Here u and v the two unknown parameters. One way for finding this u and v to solve in the xy components of the equation simultaneously, we can write in the scalar form, that is px of u minus px of v equals 0. In y direction py of u minus py of v equals 0. In z direction pz of u minus pz of v equals 0. This is the three equations. To calculate the roots of equation 1 and 2 can be found by numerical analysis methods such as Newton-Raphson method. This method requires an initial guess which can be determined interactively. The user is usually asked by the CAD/CAM software to digitize the two curves whose intersection is required. The last one is transformation. This is the very important manipulation in any CAD/CAM software. Manipulation or transformation of geometric entities during model construction or creating the model database offers a distinct advantage of CAD/CAM technology over traditional drafting methods. With transformation techniques, the designer can project, translate, rotate, mirror, and scale various entities. With the help of transformation, the user can uh, zoom in, zoom out manipulation, and move the one element from one location to another location with the help of translate tool. With the help of rotate tool, the user can rotate with respect to x direction, y direction, and z direction, or xy direction, yz direction, and zx direction. Here, mirror tool shows how the mirror command construct a symmetrical object. Scale means the user can enlarge the images or increase or decrease the size of the particular object. Transformation is also useful in studying the motion of mechanisms, robots, and other objects in space. With the help of simple transformation are usually referred as rigid body transformation. They can be directly applied to parametric representation of geometric models. To translate a model of a car, all points, lines, curves, and surfaces forming the model must be translated. One more transformation also there, that is homogeneous transformation. We will discuss in the coming lectures. With the help of homogeneous transformation, it forms a perform all rigid bodies transformation as matrix multiplications, which is a desired feature from software development point of view. We will discuss in the coming. We will discuss in Unit 3 transformation topics. This is the brief discussion about various manipulation tools in CAD/CAM software. Having completed the discussion on curve manipulation, now student able to identify the implementation of curve manipulation in CAD/CAM system. Here, various curve manipulation are displaying, evaluating points, segmentation, transformation, trimming, intersection, etc. And the second lecture outcome is analyze curve manipulations techniques in CAD/CAM. We discussed it with each and every manipulation with suitable example. The students are required to uh, read the following textbook, that is Ibrahim Jeet and Shiva Subramanian RR CAD/CAM Theory and Practice, second edition, New Delhi, Tata McGraw Hills, 2010. The reading chapter number is 4.7. Thank you for watching.